So this ham radio problem, it's been giving people trouble. I wanted to include it because this is an actual example of a problem that did happen. So we were, a couple of years ago, we were moving a tower off of a property for the ham radio club. And really nice tower. Like the guy, he actually talked to the International Space Station on this thing. But yeah, she was moving. So it's a tilt over, which means there's a little bolt on the base of it that you could put the whole tower down and then service the top of it. This thing actually went up to 89 feet tall. So right now you see that it's kind of, it's telescoped in. So this is a crank up tower, no guy lines. So you just crank the thing up, crank it back down, and then you could tilt it over to service the antennas on top. And so there was a pulley and a winch that was hooked up on the back. And yeah, it was pretty hefty. So this is the size of a kind of a small car is the weight of this. And we did break a cable tilting this thing over. This was not the original cable that went with it, but just a reminder that if you ever are working around cables, whether it's just winch on your truck or something, man, be really careful. These guys have elastic stored energy in them. So when they break, it's like a rubber band breaking, but if it snaps back, it can be very, very dangerous. So we were very lucky. No one got hurt. You can see this 55-gallon drum that was crushed like a pop can when this thing fell on it. So we had that set up to kind of just lean it over onto that, and it smashed it like a pop can. But so yeah, be very careful with cables, and it is very important to kind of look at the weight. So the weight that cable was holding, much, much more than this 2,400 pounds. Okay, so how to solve this thing? And I actually grabbed some info straight off of, so we contacted the company that originally made the structure, and we got the actual weights that were going on here. I got a ruler out. These are the dimensions of this. So you can see this bolt down here. This is where it's tilting over from. And the cable, you can set up a pulley system, and that will actually have how much of the tension is. So if you have two cables instead of just one holding it up, you get a really nice mechanical advantage there. But it comes down to the angles on this thing for trying to get this in place. So there was a real good foundation, some interesting foundation design kind of concepts in that too. Okay, so let's go ahead and walk through. This is a two-dimensional moment problem. So what we're looking at here, the axis of rotation, and these are real big bolts. This is a really nice big bolt down here that it leaned over from. And this would be the weight of the tower itself. So that was that 2,440 pounds, and that was just the tower. So you add the weight of those antennas on top of it, and it's a little bit more. Those things you put on rock climbing equipment, and you can climb up those. Don't ever climb up a telescoping crank-up tower that is up, because any minute the whole thing could fold and collapse. So you have to completely retract it before you start climbing up it. And then when you climb up it, you anchor yourself to it, just like you're rock climbing. So it's scarier than rock climbing because you're up in the air. Like there's no solid wall in front of you. It's complete air, all 360 degrees around you. So some electrical engineering stuff can be kind of exciting work. Okay, so we're going to go from the axis of rotation up to the weight. And remember, it's a cross product, right? And so what you're really after is the perpendicular distance. And hopefully you can see on this one that the perpendicular distance here to the line of action of the weight is the distance right here on the ground. So what we did is just label this axis theta W for the weight, And so this distance is going to be 5 meters, and this is the adjacent side to that angle. So this is going to be theta weight, and we're just going to do this calculation for a couple different angles, and you can then see how the tension is changing as this thing is being slowly lowered to the ground. And you want it to be slow, because if there's any accelerations in there, that's an even greater acceleration, or any kind of like sudden stops or sudden goes, like that F equals ma versus F equals 0. If you add ma into it, man, you get large tensions. Okay, so that is one side, and we're going to have, if you remember the direction that moments go, so clockwise, if you write the vector for this thing, what clockwise is doing is wrapping your hand. If you wrap your fingers of your right hand around the axis of rotation, your thumb will point kind of in the direction of that arrow. So clockwise rotation gives you a negative moment in the k direction. So this is wrapping around the k axis here. And then you also have what we'll call positive x horizontal and positive y going up for this case. Okay, so as well as the weight of the tower itself, what we have holding it up is this tension right up here. So our next R cross F, and I did grab these dimensions right off of the tower and the foundation itself. So we're going to have to figure out this little angle for the tension based on those dimensions. So that's going to be the tricky part. Okay, let's do this R part first. So we're going to need to split that position vector up into x and y components. And maybe let me come down here to a new little thing so that I can, let's just really look at this thing. Okay, so I'll use a nice dark. Okay, so this green triangle, what we have, and because of just the thickness of that tower, this angle is going to be a little bit more than what that red arrow was. And what I have it defined as is what the weight was at plus 20 degrees. And that comes from just the center of the tower where the weight is versus the edge where the cable is applied. And if you look at those dimensions, it comes out to 20 degrees. So that's going to be the part of our R cross F for the tension. So we're going to have, this was 1.5 meters right here. So this will be 1.5 cosine, and then it's going to be plus 20 degrees here. And then 1.5 sine, and it's going to be 20 degrees. Okay, so there's the positive x, rx, ry that's going to go into a cross product. And now the really tricky part is to try and break this tension into its x and y components. So we're going to have to figure out these two components of it. And I went ahead and I made this angle, I labeled it with a little t. So this is the angle right here, and we need to figure out what that is. Okay, so we have 2 meter height, and then we also have how tall this green triangle is, right? And so what's going to be left over on this side of it, this piece of that triangle, that's going to be equal to, hopefully can you see it? So it's going to be the total height, 2 meters, minus the y side of the green triangle, which was created from both of those angles. So really tricky to be able to figure figure out those dimensions. Okay, so now let's look at this other side of that triangle. And what we have, it's going to be a combination, right, of this 1.7 meters that's given on the bottom here. So there's that 1.7 meters. And then we're going to add on to that the base of that green triangle. Some of these, just really studying the dimensions and the angles is going to be the hardest part of this. So this is going to be 1.7 plus 1.5 cosine, and this is the green triangle, so we're looking at that angle plus 20 degrees. Okay, so once you can figure out this theta t, then you can split your tension into x and y components. And this is a problem that if you set it up in Excel right, you can go ahead and change this angle and it will calculate everything for you. So then you can kind of look at the scenario for different angles. So if it's going to be slowly lowered to the ground versus all the way standing up, and then think through how is the tension on that cable changing as it's slowly lowered to the ground. And it's yeah, cables are an important thing. There's a lot of applications that have cables. Okay, so I'm going to go ahead and grab a screenshot of this, and then let's head over to Excel. And if Excel is driving you nuts and you want to try this out by hand, that's fine. The first step is just huge diagrams. So get something large enough that you can label everything on it. So here we are over in Excel, and let's go ahead, instead of 12 kilonewtons, let's put in that 2020. Let's do this in pounds. So pounds is a force, not a mass. And we will start out, and what I like to do is just set this up so that we can plug in a bunch of different angles for kind of this red triangle to the weight. So this is the red angle to the weight. And if we do this right, we should be able to change this theta W to the weight and have everything else recalculate from it. So I'm going to go ahead and change this over to radians just because Excel likes radians, and make sure that you have radians versus degrees on your calculator right. Okay, so the moment from the weight, and this one is this red 5 meters. That's our R cross F. And so we're going to say that the X component of this, that's the adjacent side of that angle. So I'm going to just grab this right off of here. And then the opposite side, so that's going to be 5 times sine of that angle. And this is just a two-dimensional problem. So two-dimensional problem, a lot of problems are two-dimensional. Here's our weight. So our weight is acting down in the negative J direction, and we don't have to multiply that by gravity. It is already a force. And here's our cross product, and you can see that it's the I component of that vector that gives us the moment here, and that's going to be a negative moment, clockwise negative moment in the K direction. Okay, so there is that first piece of it. The next piece is to the tension. So let's pop in that radius first. So we're going from the axis of rotation. This green arrow is what we're after now. This is up at a different angle, and the green triangle is 20 degrees more than the red triangle. So we can go ahead, and I'm going to grab this corner, left click, and I'm dragging that down so that now it's going to grab the radians of that, and we can get our R cross F. So equals 1.5 times the adjacent side of the green triangle now. Make sure I grab the right angle here. And here is the 1.5 times sine of this green triangle here. And you'll notice I can change this angle and it's changing everything. So it's all coming back to what that angle is and what the weight is. So I can change things around and I can see how everything is going to react to changing that angle. So the small angle, that's this thing almost laying on the ground. 0 would be laying on the ground there. Okay, for the tension, if I were to put in the equations for this, so I would have something pulling to the left in the x-axis, and that is adjacent to that little tension angle. And then I would have the opposite side. So let's see if I can figure out what those angles are. And if you have the same thing in both of these, what you can do is I can actually pull that tension out of the cross product and just pull it to the outside. So the whole cross product is multiplied by the magnitude of that tension. And that way I can just figure out what the angles are. And the last thing I'm going to have to solve for that tension. And this thing, just like for equilibrium, so statics, everything adds to 0. And that applies to moments as well as forces. So the weight trying to pull it clockwise is going to have to equal the tension pulling it counterclockwise. So we're going to have counterclockwise, clockwise moments here balancing each other out. And this cross product multiplied by tension is going to have to give us that balancing moment. Okay, so let's try and figure out this little teeny tiny angle here. And to do that, what I'm going to do, that's a pretty big equation. So rather than trying to cram it into one thing, I'm going to go ahead and give myself one more row here. And I'm going to call this, instead of the big T, I'm going to call it little t. So this will be the angle right up here. And to get that, I need the height, that's the opposite side, and I need this adjacent piece. So let me just say the X for the tension, Y for the tension. I'm just going to do those in another little cell here to make it a little bit easier. So this in the X direction, remember, is going to be 1.7 plus the base of that green triangle. So 1.7 plus, and the green triangle was 1.5 times cosine, and that's going to be the angle, the green angle here. Maybe I should redo the color codes here. So this is for the green triangle. This is for the red triangle, and then maybe we should call this the blue triangle up there. Okay, so there's the X component. Let's just make sure we have that in right. 1.7, and it's 1.5 cosine of the green angle, which is this guy, plus 20 degrees. Okay, so that's the X component. The height, so that's going to be the total height, 2 meters, minus this side of the green triangle. So I'm after this little red guy here. So I'm going to say minus 1.5 times sine of this angle right here. See how you want to kind of break these big equations into pieces. So I wasn't going to type all of that in over here. Just take it, that's engineering. Take it one byte at a time. Okay, so now I can say the inverse tangent of opposite over adjacent, and Excel does everything in radians. So at the end, if we want to change this into degrees, there we go. Okay, so now we have our angles, I can come up here, and I'm not getting my tension in here yet. So really it's tension cosine theta, tension sine theta. But this is the last thing. So I'm just going to put in the cosine and sine piece of it. So the x component's pulling to the left of that tension, and it's pulling up. So this is the opposite side of that angle that we found, pulling to the left and pulling up. And if I crank through this guy, so this is not the full moment, it's missing, I have to multiply all of this by the tension. So we're going to go this times tension equals 11. So that means our tension is equal to this divided by this. Okay, shall we check it out? And just to be sure, I'm going to just copy and paste and just, let's just be sure here. So I'm going to say here is my position vector. Here is that angle times tension. Angle times tension. And if I crank through the cross product, so here's blue times red minus purple times green, we get 11784.3. Woohoo! Okay, so we got it in there right. So the next piece of this, and really I don't need to actually copy and paste this, but think about how is that tension going to change as I get closer to the ground. So it's already quite a bit more, right? The crane only weighs 2,400 pounds, and the tension is an order of magnitude bigger than that. As the angle gets larger, so this is standing it up, pulling, 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 making it stand up. And what is happening to the tension as it stands up, and why? Ooh, do you know what? For our moments, this is actually currently in pounds per meter. I just remembered all these dimensions. I did do those in meters. So let's go ahead and change this around again. Excel has a really cool little convert function. So let me remind you guys of those if you haven't used convert before. So I'm going to say convert 2440 from, now there's pound mass and pound force. So we're going to say that is a pound force to kilonewtons. It should be around 10 kilonewtons. Okay, so there's a better there's a better moment that's actually in kilonewtons times meters. That's a better thing. Okay, so think this through. Lots of ways to modify this. You don't want to just solve for answers. You want to think of design. How could this be designed better to minimize the tension? And the answer is you don't have to attach it here. You could attach that cable up higher or down lower. So that would be a really good design problem to tackle, to think about where to attach this cable. Chances are at some point in your life or career, you're going to be hauling something with a cable, and thinking through this now and recognizing the best ways to attach cables and what that's going to do to the tension that's in that cable, just where you position the thing. That's an important question to think through. So hopefully that was an interesting example of a 2D moment problem.